All right, today, guys, we're going to be talking about solutions. Oh, you know what? Sorry for the Christmas one. I think I usually do this lesson after Halloween, but it says, "Merry nothing, same to you." That's the atheist Christmas. All right. Solutions. Solutions are homogeneous mixtures of two or more pure substances, and you can have any mixture of gas, solid, liquids. But generally speaking, your typical solution that you work with is a solid, usually dissolved in a liquid. So the one that's in less abundance would be the solute. The one that's in more abundance is the solvent. So here, this is in purple. The intermolecular forces between solute and solvent particles must be strong enough to compete with those between solute particles and those between solvent particles. So what this is showing is like for example, salt, right? Or ionic compound, alternating positive and negative ions, okay? So you could put it in water and perhaps it's insoluble. It would be insoluble if the attraction between the ions is greater than the attraction that the ions have for the polar water molecules. But if it does dissolve, this is what's happening. As a solution forms, the solvent pulls solute particles apart and surrounds or solvates them. So here we're showing the ionic compound dissolving, and you can see the ions separate. That's why it appears as though when salt you put in water, it disappears, because you can't individually see, or you can't see individual ions. And you remember what it is about water that makes it the universal solvent, essentially, is its polar characteristics. So the partial negative end of the water molecules will be attracted to the, let's say, a positive ion, and the partial positive end of the water molecules will orient themselves around the negative ions. And so you can see, ultimately, this could show, complete solvation, in which the entire solid has been converted to the aqueous dissolved condition. If an ionic salt is soluble in water, it's because the ion dipole interactions, that's what we have, right? It's an ion dipole. You have the dipole from a water molecule, di meaning because it's got a positive negative end, is attracted to the ion. It's strong enough to overcome the lattice energy of the salt crystal. You guys remember, the lattice energy is the energy needed to separate out the ions within an ionic compound. So basically, if the attraction between the water molecules and the ions is greater than the lattice energy, then that ionic compound will dissolve. Three processes affect the energetics of solution, so you guys think about it. Here's essentially what's happening when something dissolves in water. First, there has to be a separation of the solute particles, right, the ions, for example, an ionic compound. Then there also has to be a separation of the solvent particles, right? Think about all the water molecules. Before you put the salt in there, the water molecules, right, are attracted to each other, so those kind of have to separate. And then you also have the interaction between the solute and the solvent. So it's like really three things going on. Solute has to be separated, the solvent particles have to separate, and then the solute and the solvent particles come together and interact together. So this is kind of describing the energetics of that. So think about our original solvent and solute. Here, once again, I think it just helps to have little visuals to see what's going on. So I got my solute and my solvent, okay? So let's say I put my salt in there, okay? So what has to happen first is the solute particles have to separate. And you guys see, look, we're going from a certain enthalpy state. You guys remember enthalpy is the potential energy in the initial reactants. And so then we go to a higher energy state. It requires energy to separate out, right? Obviously, you guys remember the lattice energy to separate out the ions within the ionic compound. So that requires energy. Then it also requires energy. You notice that, right, we have a positive delta H. That means energy is absorbed. It requires energy to separate the solvent particles, right? Because the water molecules they're in close proximity to each other. Once you put the salt in, you have to, right, there's energy required to overcome the intermolecular forces holding the water molecules together. That requires energy. Now, when the separated solvent and the solute particles interact, that is an exothermic process. Notice we're decreasing in delta H. Energy is given off as these attractive particles interact with each other. And then so we look overall, let's say we end up right here. This is my dissolved salt solution. You guys will notice the dissolved salt solution is lower in energy than the original solvent, water, and salt that I would have had initially. And you guys, that's often the driving force. You guys remember, things tend to go to they tend to interact in such a way to lower their potential energy state, right? That's exactly why water flows downhill. Water starts at a high energy state, it's just going to naturally go to a lower energy state. So what happens is, right, so what we see here is there was energy required to separate the molecules, there was energy given off in the interaction of those particles, and you can see more energy was given off than was required to separate it. So overall, what kind of reaction would this, or what kind of process would this be? It would be exothermic. We went from a higher energy state ultimately to a lower energy state, right? Energy is given off, usually in the form of heat. That is an exothermic process. That's typically the process that you would expect when things dissolve in water. However, you can have a situation in which you have an endothermic process. You guys, I wish I could show that, well, here. So for example, you could start with a solvent and solute. Once again, it requires energy to separate the solute, requires energy to separate the solvent. Then when those come together, energy is given off. But you see, less energy is given off than the amount of energy that was required to separate the molecules. So you could end up with your solution, and now look at your solution. The enthalpy of your solution is actually higher than the original enthalpy of the reactant you started with. That would indicate that it absorbed energy from the surroundings. That would be an endothermic process. So what would you guys expect in that situation? Like, for example, that's actually what happens with ammonium nitrate. If I take ammonium nitrate, and you guys, I just had ammonium nitrate, not that it would have been a great demo anyways, but basically I could put ammonium nitrate in here. The district took it because I guess it's a harmful thing, so they're kind of taken from the chemistry classrooms. But I would put ammonium nitrate in there. Let's say I have my water at room temperature. It's about 23 degrees Celsius. I put ammonium nitrate in there. If we know it's an endothermic process, what do you guys think you would observe on the thermometer as the ammonium nitrate's dissolving? Endothermic process, right? You guys see, it's basically absorbing heat energy from the surroundings. You would expect the temperature to go down, right? Because the heat energy, the kinetic energy of the surroundings, right? Some of that energy, that heat energy, is being converted to stored potential energy. So it's drawing energy from the surroundings. You would expect the temperature to go down. So that's typical of an endothermic process. So the question might be, well, why do endothermic processes occur? You guys look, we're going from a lower energy state ultimately to a higher energy state once ammonium nitrate dissolves in solution, because there's another driving force behind naturally occurring processes besides just a lower energy state, which helps explain why endothermic processes occur, even though you guys know that happens much less frequently than exothermic. And it all has to do with randomness. Things tend to go to a state of more randomness or disorder. We're going to talk about this second semester. I don't want to talk too much, but it's like if you took two liquids, you put them together, you wouldn't expect them to remain separate, right? You might say that's more orderly. When you guys just expect due to random molecular motion that they're going to mix. That's just going to be the naturally occurring process. So even though there's no energy transfer here, the process will occur from a more ordered state to a less ordered state because things tend to go toward more disorder. That's a new term, entropy, but we're going to talk about that second semester. So even though enthalpy may increase, remember that's the chemical potential energy of like an endothermic process, the overall energy of the system can still decrease if the system becomes more disordered. So that's another factor you have to take into account. Okay, so we have a few terms here. You can have what's called a saturated solution. If we have a saturated solution, that means the solvent holds as much solute as it can possibly hold. You guys know I could add, I could just keep adding salt to this solution, to the water, but eventually you guys, when you guys agree, no more salt is going to dissolve. Any extra salt I add is just going to fall to the bottom. We would say that that solution is saturated, right? There's only so many salt particles that the water molecules can surround or solvate. And notice it says at that particular temperature. So if we change the temperature, then we can change the solubility. An unsaturated solution would be, as you might expect, it's when there's less solute dissolved than the solvent can actually hold, okay? So this is what I want you guys, this is very, very important, guys. You guys write this down. Like dissolves like. Substances that have similar chemical structures are going to have attraction for like chemical structures, and then that would aid the dissolution process. Polar substances tend to dissolve in polar solvents. Non-polar substances tend to dissolve in non-polar solvents. Very, very important to note this, guys. In fact, this is a technique, utilizing this is what a lot of chemists use in order to separate out different compounds in chemical labs. So for example, Here, you guys, we have alcohols. You guys see it, alcohol is a carbon-based substance with an OH group at the end. That's what an alcohol is. Here's the alcohol that you're probably more familiar with, ethanol. That's the drinking alcohol in like beer and wine and stuff. That's a C2H5OH. It's a 2-carbon alcohol. But you can see the alcohols are getting larger and larger. Hopefully you guys can see this on the video screen. You know, it's showing these different alcohols and their solubility in water and in hexane. Now you guys will notice this. Water, you guys got to remember, is a polar compound. You should know water's polar. You guys remember hexane from a previous demo we did. We know, and you guys remember, all pure hydrocarbons, they're non-polar, okay? So hopefully you guys are seeing what this is showing us. This is showing us alcohol, when that's like an infinity, basically the methanol here, it dissolves readily in water. That's what that's showing. But notice it only dissolves minimally in hexane. That shouldn't be surprising just based on what we're saying here. Water's polar. You guys, what does that tell us about the methanol molecule? That's polar. And the fact that that's polar and that's polar explains why it so readily dissolves in water. Yet hexane is non-polar, so the polar methanol does not dissolve very readily in. But now look, now it's showing these ones dissolving readily in both, so that's kind of at least different. Maybe we want to look at the opposite extremes to kind of get a better understanding of this. Now look, as the alcohol gets larger, so you've got butanol, which is 4-carbon, pentanol, 5-carbon, and hexanol, which is 6-carbon. Now hopefully you guys are realizing this. Look, in general, you could say all alcohols are polar, right? Most of you guys, right, I said, hey, look for a highly electronegative atom like oxygen. But if you think about it, as the alcohol gets larger, as the hydrocarbon chain, wouldn't you guys agree the hydrocarbon chain is really a non-polar component of that overall alcohol molecule? Really, what's making it polar is this OH group. Wouldn't you guys agree, as the carbon hydrogen component of the alcohol increases, wouldn't you agree that the alcohol becomes more and more non-polar, right? Because you see how it's going to be more dominated by the hydrocarbon portion rather than the little OH group. And so what we're seeing as the alcohol size increases, it's becoming less and less polar, and therefore what happens? Its solubility in water decreases more and more as the non-polar component begins to dominate that compound. And then what happens, right, the more non-polar it gets, you might expect the more soluble it would be in a non-polar compound like hexane. All right. Okay, factors that affect solubility. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another. That's kind of what we just observed when we said like dissolves like. So for example, look at glucose. Here's glucose. Hexane. They call it cyclohexane because it can actually form a ring, and then glucose in water actually forms a ring. You guys remember glucose is C6H12O6, and that's kind of this funky, these are carbons right here, okay? What's it saying? So you guys should be able to look at cyclohexane and go, oh, that's, these are all carbons, by the way. Oh, that's nonpolar. And glucose, look at all these OH groups, oh, that's definitely polar. So what would we expect about glucose? Let's say we put both of them on water, what would you guys expect cyclohexane to do? It wouldn't mix, right? It's not soluble in water. But you would expect glucose to be highly soluble in water due to the fact that it is polar, just like the water molecules. Check this out, guys. We've got different vitamins. Here, for example, is vitamin A. You guys know you guys need vitamins. Those serve as enzymes that help, metabolism and helps, right, chemical reactions happen in your body. You guys can see it's a pretty complex molecule. But you guys, and if you guys look at vitamin A, you'd have to looking at it overall, what would you have to conclude about vitamin A? Obviously it says it right there, but look at the main component of vitamin A is just this big hydrocarbons, all these hydrogen carbons, and then it has this little OH group at the end. For the most part, you probably have to conclude vitamin A is pretty non-polar, right? Therefore, what do you expect? It's going to dissolve in things like fats. You guys think about where have you guys heard of vitamin A? I know whenever I drink milk, they always say vitamin A and D fortified. Primarily if you have whole milk, not so much non-fat milk. Vitamin A, as a non-polar compound, you guys are going to expect it to dissolve in non-polar solvents. Well, fat would be, fats are a lot of hydrogens and carbons as well, so just think fats are pretty much non-polar. So it's not surprising you're going to see vitamin A in fats, like animal fats, things like that, right? And obviously that's where milk comes from, the cow, animal fat. But now look at that, compare vitamin C to vitamin A, right? Look, it's got hydrogen and carbon. You guys remember most all organic compounds are going to be carbon-based. But look at how many more OH groups there are. you would conclude that vitamin C is much more polar. In fact, you would say vitamin C is a pretty polar compound. Therefore, it's not surprising, where do you guys find vitamin C? Don't you find it in citrus fruits? It's going to be soluble in water, right? So you're going to find it in a lot of water-based fruits. Solubility of gases in water increases with increasing mass. So that's just something to note, guys. Think about, you're right, you can have gases dissolve. We've been talking about solids dissolving in water, but you can also have gases. They're saying the larger the gaseous compound, the more it's going to stay dissolved. And that would be because larger molecules have stronger dispersion forces, right? You guys remember, the larger the molecules, the more electrons it has, the more polarizable it is, the more attraction you're going to have between those, and therefore it's going to be less likely to escape, from from your water. Just think about gases dissolved in there. It's going to be less likely to escape, so therefore it's more soluble. Gases in solution. It says the solubility of a gas in a liquid is directly proportional to its pressure. Okay, so the solubility of a gas, so how soluble it is directly proportional to the pressure of the gas over the liquid. So what this is showing is, right, here we have a piston, we're pushing down on the gas, right? So we have the same amount of gas molecules there. And when you guys agree, in a closed system, you're going to have gas molecules escaping into the gas phase, and you're going to have gas molecules dissolving into the aqueous phase. So as we push down on this, we're decreasing the volume. Now those same amount of gas particles are in a smaller space. When you guys agree, the pressure increases. What's the result? You're going to have more gas molecules dissolve, right? And that's in part, right? When you guys agree, that's why, right? Whenever you have soda or a can, how do they sell it? They don't sell it open. They're going to have the cap on to maintain the pressure of the gas. That way, obviously your soda stays fizzy. So obviously, if you want your soda to stay more fizzy, you're going to keep the cap on, which kind of maintains the pressure of the gas over. Therefore, more molecules of the gas will dissolve in the water. So, you guys, based on this, I'm thinking you guys could probably come up with a formula. It's a pretty simple formula. Think about how you could translate this mathematically. The solubility of a gas in liquid is directly proportional to its pressure. And think about that. I would like if you guys could pause it and try to write out what the equation might look like. Here it is. Basically, it's really simple, guys. The solubility of a gas is equal to, you guys, K is just, remember, small k is just a constant. It's what you put there to make your equation work out correctly, and it's and that's the pressure of a gas. So you guys see, it's a really simple thing. Well, if this is a constant, well, wouldn't you guys agree? If I increase the pressure of the gas over the liquid, so that this value becomes greater, what happens to this value? The solubility becomes greater. If I decrease the pressure, how can you decrease the pressure? Just remove the lid. As you decrease the pressure of the gas over the liquid, what happens to the solubility? It decreases. So this would be Henry's law. Very, very simple, guys. The solubility of the gas is directly proportional to the pressure. That means if I double pressure, I'm going to double the solubility. If I half the pressure, I'm going to half the solubility. Okay, and then that's just describing what we had just stated. You know what? I'm wondering if you guys could come up with, you guys think about it. Let's say we have our soda in here. First of all, we said we want to cap it, okay? You already might, right? We always want, we don't want warm soda, and we're going to talk. Oh, you know what? I'll just wait on that. Maybe I'll come back to this. Okay, so going back to these are all solid compounds, okay? And we're graphing the solubility compared to the temperature. And so, what should you guys notice? What's the general trend? What do you guys notice about all these? They're all going up. What does that indicate? The higher the temperature, the higher the solubility, right? And you guys, we kind of knew that. You think about when you're making hot chocolate. If you're going to make hot chocolate, are you going to put the cocoa in the cold milk and then heat it up, or are you going to heat up your milk and then put the cocoa in? When you guys do the latter, when you heat up your milk first and then put the cocoa in, because you guys know when you put cocoa in the cold milk, you guys know how it kind of just stays at the top. The solubility is very low. But when you put it in warm milk, the higher the temperature, the higher the solubility. And you guys, that's simply due to random molecular motion, right? The higher the temperature, molecules, right? Just think about water. That's their typical solvent. Water molecules are moving faster. They're going to interact more easily with the solid particles and solvate that. Therefore, you'd expect a higher solubility. But the opposite is true of gases. Notice these are all gases: methane, oxygen, carbon monoxide. You see, as you increase the temperature, the solubility of the gas decreases. You guys, that's for the same reason. But in this case, think about, carbon dioxide. Let's say this is carbonated water, right? You can imagine as you heat it up, aren't you increasing the kinetic energy of those gas molecules? Don't you guys, when it makes sense that those gas molecules are now going to more easily escape the liquid phase, therefore decreasing the solubility. So you guys putting that all together, just for a very real thing, you think about it, obviously what is it that makes soda soda? The fact that it's fizzy, right? If it's not fizzy, then it's not even soda. You might as well just drink like Kool-Aid or something. So anyways, taking everything we just said into account, taking this into account, I want you guys to think, what would you guys do with your soda to keep it fizzy, to keep the carbon dioxide dissolved in there when you have it at a lower temperature? So you're going to put this in the refrigerator. Remember we said with Henry's law, the higher the pressure, the higher the solubility. So what are you going to make sure you do? Aren't you going to make sure you cap it, right? To keep the pressure of the gas over the liquid, therefore more of the molecules will dissolve in the water, increasing the solubility and increasing the fizziness. And then there's one other thing, and I think I had talked to you guys, or we had talked about this last year if you were in my class. There's one other thing you could do. Obviously you want to keep your soda cold, keep it in the refrigerator. You want to keep but let's say you drank some of it, right? And you guys know that's the problem. You drink like some of your 2 liter, you're not going to take it to the head, you're probably pouring it, be a civilized individual. Then you're going to put the cap on, and then you're going to put it in the refrigerator. But then you guys know, even maybe a couple days later, it could already be flat. And so I was kind of wanting you guys to take a pause here to think, what could you do to increase or to maximize the fizziness in addition to not only capping it, and also refrigerating it? When you think about it, how can you increase the pressure of the gas over? Remember, Henry's law says the greater the pressure of the gas, the greater the solubility. Think about what could I do? So you have a half drinking bottle, what could you do? And that seems kind of weird, but you could just crush that bottle. And you guys should remember from gas laws, now I have the same amount of gas that was in there, right, over my soda, but now all those gas molecules are in a smaller volume. If you decrease the volume, you're going to increase the pressure. The pressure of the gas over the liquid is greater. According to Henry's law, more of those particles are going to dissolve. It's going to be more soluble, and it's going to be more fizzy. Little note there. All right, guys. Thanks for joining me. We'll see you guys next time. Bye.